Right. MPLS stands for multi-protocol label switching. Multi-protocol label switching, MPLS. Now, why the name MPLS, multi-protocol label switching? Anyone has got any answer? Tell me, please.
Have you seen a sheet both the side printed? Like it will be like a Sunday school sheet.
Okay, but I agree on all the thing except one point that you said in the beginning. MPLS is not old. MPLS is not an old way of forwarding the packet. MPLS got added very recently. You can say like after 2011, it gained more popularity. It is not that old, sir, as you say, and this is not a routing protocol also. Did you say routing protocol? Okay, you said like on those days the routers were not that efficient, something like that, right? For routing. Hmm. Okay, fine. So that's your your imagination, I think. Yeah, the routers were not that fast like today, but that's not the reason for MPLS. MPLS definitely reduces the load. I agree. Reduces the load, the CPU. Uh, there's no doubt in it. But the main reason of MPLS, multi-protocol label switching, is not only to reduce the load. You see, if they want to increase the process, they would have done increasing the processor. Then there won't be a need for MPLS. Right? See, if the CPU is the problem, after increasing the power of the CPU, they would have thrown MPLS. Why we still use MPLS? Do we still use MPLS? Yeah. So we have very super computer like routers today. Then why are we still having MPLS? So that is not the reason. Multi-protocol label switching is a smart way of packet forwarding. Yes. So we have improved the routing in a smart way. How can I say in a simple way? Okay, let me tell you like this. In olden days, even today in India, someone have to show their ticket. Someone have to show their ticket if they want to travel in a train when the ticket checker comes. But that is not the way many grown-up countries. They have a QR code on your cell phone. You get a QR code. You just get into the bus or car or train. You show the QR code that tells who you are. There is no need for uh, checking the date of travel, checking the passengers, the age, name, address proof, nothing. You just show your phone. They bring a scanner, and if the scanner shows green, they go to the next passenger. Right? If the scanner shows green, you're verified. Smart way. smart way of checking the ticket. Likewise, MPLS is a smart way of routing packet. What you said is absolutely right. Between layer 2 and layer 3, uh, layer is added. You can see this in two different angles. So, one, you can say you are adding complexity to your header. Already you have 7 layers. Now you are adding another layer. What is this? You are making it too complex. That's one approach. But if you go deep and see, you will agree that even though there is a slight uh, complexity added, but the problem that it resolves is a big one. So MPLS is not making the network more complicated. It makes routing easier. Label should change, which means you don't want to do IP routing. Yes, that's what MPLS does. We always do IP routing. By enabling MPLS, what you are saying is, no, I don't want to do IP routing. I want to do label switching. Meaning, I want to forward the packet the same path which the IP routing can take your packet. Now it's taken here by the labels. Same path is given, but earlier it was decided based on the IP address, the destination IP address. Now no more, it is going to be based on your destination IP address. When the router processes, it checks the label and it knows the exit interface. It knows the forwarding path. It knows the destination. But the router did not check the IP packets destination IP at all. It did not check at all. It did not check the layer 3 packet, the layer 3 header of the packet. Without checking layer 3 header of the packet, by just looking into the label, routers now know the destination, the path, the exit interface. See, what do you get from the routing table? You get the path, the exit interface for destination. Now, MPLS can give the same info what you used to get by looking into the routing table. MPLS has got a control plane, the MPLS forwarding database. So using the MPLS forwarding database, now router can send the packet to the next hop by picking the right exit interface. We used to call it as routing earlier because it was purely based on the incoming packet destination IP we were designing. But now the routers are designing based on the incoming packets label. The path is determined, the exit interface is determined, the next hop is determined by looking into the label in the packet, not the destination IP address. Now you may say like, you say that it's from IP address, it is looking into the label. Why not IP address? Why you are adding another one label? What is the benefit? Anyhow, you have to look for label. You have to look for label. We were looking for IP. Now you are saying we look for label. What makes the difference? Anyhow, you have to do the look. lookup on every packet. It's true. Router have to do a lookup. When you enable MPLS, it looks for label. When there is no MPLS, it looks for layer 3 network layer. Now it is going to look for MPLS layer, which is called as 2.5 layer. It is looking for MPLS layer. Earlier, it used to look for network layer. It has to do a lookup. Why you add this one? That may be a question. Why are we adding? Anyhow, router have to look into every single packet's MPLS header. Earlier, it was looking into this one. What makes the difference? The difference is this IP routing header is too big when you compare to MPLS header. What is the size of an MPLS header? Only 32 bits. I'm not even telling bytes, just bits. The entire header itself is only 32 bits. But if you take any layer 3 header, you will see 64 bytes sometime more. Let me show you one profile here. You see here the size, you see the total length 519. See the header length 20 bytes, it's not bits. 20 bytes of layer 3 header. This is very small, okay? Sometimes you see bigger than this. 20 bytes. 20 bytes. In order to know one single entity called destination address, on every single packet, the router need to process 20 byte of info. The main story is this. When you go through the IP header of every single packet, it is going to take a lot of time and CPU. Instead, you just go through 32-bit size header to know the destination. Routers are now going to read only 32 bits. So this 32-bit can give the same information that you will get after reading this whole big header. That's the main story. Because I have only 32-bit to read to know the destination, 32-bit is same like what the size of an IP address. You don't need to read this version, header length, and DSCP, field, total length. All these are not needed to know the destination. Now, in that 32-bit of MPLS header, let me show you that also. You see, instead of you reading this 20 byte to know just one single info for destination address, you are going to read only this much. You see, layer 2, layer 3, sorry, layer 2.5. When you read this, you will know the destination and why I should go here, not necessary. You don't go reading this internet layer in the OSI, in the packet, incoming packet. So it reads only this much. In that, in the 32-bit that I was talking about, 32-bit, this 32-bit, the first 20-bit, you count and see this, 4 times 5 is 20. This 20-bit out of 32 is for label. See, label number 16, meaning what? This bit is on, that is why it is 16. 1, 2, 4, 8, 16. And then you got 3 bits of QoS, which can also be called as MPLS traffic engineering bit, TE bits, which is also called as experimental bit. 3 bit only. Out of this 32, 3 bit. 20 bit is for label. And then just only 1 bit, it can be 0 or 1. If it is 0, then that is not the bottom of the stack. If it is 1, it is bottom of the stack label. You see how many MPLS header you see? Only 1. And this is the final one. That is why it is 1. But when you see the other header, you got 2 layers of MPLS. And the router which is processing it, it knows that this is not the bottom label. Bottom label is the final label in this header is 507. How? Because the bottom of the stack is 1. This is a VPN layer. This is service layer. I'll explain you the service layer, VPN layer a bit later. But here what I'm trying to explain you here is you just got only 32 bit, in which you have 20 bit of label or label marking, 3 bit is for the keywords. Just 1 bit is to tell the router whether the layer that you are processing is the final layer of MPLS or above layers. It's not final. 0 means it's not the bottom of the stack. 0 means you have one more layer of MPLS to process. So only 1 bit. And then see in layer 3, now you are trying to avoid layer 3, isn't it? You are trying to avoid layer 3. In layer 3, TTL is very important. So if you avoid looking into layer 3, the TTL will be missing for you. TTL helps to prevent loop in routing domain. So, how MPLS is designed? It copies the TTL from the IP header while entering into the MPLS domain. I repeat, as the traffic enters from IP world into the MPLS world, that one entry router, that one router where the handover happens from IP to MPLS, that router is called ingress LSR router. LSR means label switch router. The very first LSR router, label switch router. It's not a special router. I'm not talking about some series. That's a link for the router that is enabled with MPLS. So that ingress router is the one which is going to inject this header to the packet. That router which injects the MPLS header, it copies the TTL that is there in this layer 3 into this MPLS. As the packet jumps from one LSR to other LSR, this will get decremented. And on the egress router, what is the egress router? The router where the packet is again handed over to the IP from MPLS. In the egress router, this decremented value will be copied to the IP. By doing so, we prevent loop even after enabling MPLS. So now, if you want to have up to 255 as TTL, then number of bits that you need is 8. And if you add this and see, you get 32. The total size of MPLS header will never go more than 32. It's only 32. Now you may say like, see, why are you going with 132, another 32? Even if it is 232, it is only 64 bit. You remember when I showed you the previous picture here above, it's 20 bytes. You're not reading 20 bytes. We have just read 64 bit, 64 bit to provide even the special service called MPLS Layer 3 VPN. So for normal routing, you need only 32 bit, yes, only 32 bit. In order to provide an additional service like LP VPN, you added another layer of MPLS. It's not for normal routing. You will be doing the same thing if you are doing GRE tunnel. When you do GRE tunnel, what do? You know, you add like this two layers of layer 3, 20 byte, another 20 byte. Here we have not added 20 byte plus 20 byte. We have added just 32 bit plus 32. Not bad. Any VPN service definitely will add another layer. So even when you do this advanced feature like MPLS layer 3, you're not adding much to your header. Only 32 bit you add additionally, and you don't take much time to process because in total you're going to process only 64 bit. 32 plus only 64 bit. You see, so MPLS makes your routing decision taken very quick on each routing. Now, for MPLS, not only on the header of the packet, you see, this is the packet that is incoming to the router. Not only when you enable MPLS on this router, let's say there is another router here, MPLS here, enable. When you enable MPLS on the router injects a layer, inserts a layer of 32 bit, the MPLS header. So that is here. And here is layer 3. Here is layer 2. Now, not only this happens, even on the routers, there is some alteration done to the forwarding database. Usually, the routers will refer the set table. The set table is routing table in a layer 2 buffer. Routing table in a layer 2 buffer, that is set table. Now you see, when you enable MPLS, the set table also gets the outbound label. What label? Outbound. Earlier, we used to look into the set table and say if you want to go to 3333, you need to go via Ethernet 0 and you need to go to 10.0.0.3. Now, to that, you also have a label now. For you. So, set table has got a label now. So, before sending the traffic out, the set table inserts this 40 and sends to router 3 with a label. That is how router 1 also inserted this label, let's say label number 30. When router 2 received label number 30, it understood that the destination is 3333. So I need to put label 40 and send it to router 3. Don't go in deep into those areas now. What I'm trying to say here is the size of the header of MPLS is only 32 bit. So you don't spend much time in reading the layer 3 header anymore. See, if it is one packet you can do, millions of packets you need to process. Every router need to process that minimum 20 byte, millions of packets. Now you are just processing only 32. And because now you're going to move forward the packet based on labels, the forwarding table which was there before called CEF table gets the label. Otherwise you cannot move. The forwarding database which you usually use for forwarding the packet should be aware of the label. So even on the router, the modification is done to the CEF table, which is also called as forwarding information base. So when you enable MPLS on a router, what all happens? For every single destination on the router, a label will be assigned. And the label will be distributed by using a protocol called LDP. Label distribution. Using LDP, the labels are distributed. And the CEF table gets updated with the distributed labels. So now when a packet arrives with simple IP header, the ingress router, the very first router, what is that router called as? LSR, label switch routers. LSR. Each router is an LSR. Wherever you enable the MPLS, those routers now get a new name called LSR. Now the ingress LSR will inject this MPLS header. Egress router, let's say this R3 is connected to the customer. To the customer, it will not send with the MPLS header. It will pop the label. It will here push the label. Here on the egress router, it pops the label. And only an IP packet will be sent here with the TTL decremented. Right? Now what happens in the middle router is swapping of labels. It came with label number 30, but router 2 was putting label number 40 to the header before sending to router 3. Because that's the label it learned through distribution, which we'll be seeing in depth in our next class. See, MPLS, the simple MPLS story is not that big. Whatever I have said, so far it already covers 50% of simple MPLS story. MPLS, I asked you what is MPLS, you said multi-protocol label switching, and it works in between label layer 3 and layer 2. You're right. But what is the benefit of this? Are we adding more complexity? Not at all. We are reducing the burden on every router. How? By providing a label to identify destinations so that there is no need to sweep the entire layer 3 header on each packet. Right? So, MPLS fastens, quickens the forwarding of traffic. We also learned that there is a protocol called LDP needed to distribute the labels among the routers. So, in this, what you understand is MPLS is not only generating labels for every destination on every router, it also distributes the label to all the routers. Why it need to be distributed? We'll see that in the next class. But there is a need for a distribution. For that, the protocol used is LDP. This protocol initially it will use UDP, then it will switch to TCP, and the protocol ID is 646. TCP 646. Now Cisco also got another protocol equivalent to LDP, which is called TDP, Tag Distribution Protocol, which uses only UDP, and the protocol number is 711. TDP uses TDP uses UDP 711, Tag Distribution Protocol. Both are good, other than these differences in port number and the TCP. But everyone is using TDP. Why? Because you need to have only Cisco routers to run TDP. You may have TDP here and LDP here. Nothing wrong in that. You can do that. But I cannot have LDP in one end and TDP in other end. Not possible. Both ends of the wire should run the same distribution protocol. And we also saw the size, the 32-bit MPLS header size is again segregated into 20 bit of label, 3 bit of QoS, 1 bit of bottom of a stack, and 8 bit of TPL. Any questions so far? No. MPLS is widely used an industry standard and RFC standard protocol. In Cisco, we have additional protocol to distribute the label called TDP. The other vendors only knows only LDP. Now, even in Cisco, when you enable MPLS, TDP is not enabled by default. Only LDP gets enabled. So no need to worry about TDP because TDP we don't use. Even Cisco don't use it, even though it is Cisco's idea of distributing label. Cisco itself have made LDP as a default. LDP is not Cisco's. LDP is industry standard distribution protocol. And again, you are not going to enable LDP. When you enable MPLS, LDP gets enabled. And now, coming back to the first question that I asked, what is MPLS? Multi-protocol label switching. Why it is called multi-protocol? Because it can work in any layer 2 environment. If I have a serial wire, HPLC has an encapsulation in layer 2, or PPP has an encapsulation, or ATM, ATOM, or anything you have as a layer 2, MPLS can work. Multi-protocol. Not only that, MPLS provides label to routes that are found in routing table. The route can be given by OSPF, the route can be given by a RIP, the route can be a static route, whatever. Whatever the protocol might have given the route to the routing table. For all those destinations, MPLS can provide label. And from there on, only label will be used for packet forwarding. Right? So with this, I want you to ask questions. Whatever you have learned from me today, if you will have any question, please ask. Mhm. The increase router, that LSR router, label switch router, the increase router injects or pushes the MPLS header with the label. And when it pushes, it copies the TTL value of the packet from the IP header to the MPLS header. And as the packet jumps inside the MPLS domain, for each jump, it is going to reduce the TTL by 1. And on the egress router, it copies the TTL from the MPLS header back to the IP because it is going to pop the MPLS header. All right, that's all. We are going to see these things live in my demo session. in our next class. There you will understand the distribution of label much clearly. Any other question? Yeah. Forwarding information base is a table which is usually referred to decide the exit interface and the next router. In Cisco, we call it as CEF, Cisco Express Forwarding, but the industry call it as FIB. And we have a we will have labels in it. We call it as LFIB, label FIB, label forwarding information base, because the FIB now got a label in it. L. All right then.